Here we're going to go over this one problem on the explicit function theorem. Excuse me, the implicit function theorem, I should say. This is a problem on the implicit function theorem. Again, we have this problem here. Sine xy minus y squared plus x, either x over y squared is 0. And so this defines a function of x, and use the implicit function theorem to find dy dx. So once again, keep in mind what we want to do. We want dy dx. Again, there's always a negative. And we want this to have our function df dx in the numerator, df dy in the denominator. Again, if you, as a memory tool, you can think of maybe flipping this over, doing the reciprocal of this and multiplying, and the delta f sort of cancel. In reality, with partial derivatives, these parts never actually cancel, but you could sort of use that as a memory tool. And you'll notice if you flip this over, and if you imagine that they could cancel, you would have dy dx over here. So it's a way to remember what order that these go in. And so now we want to find, so again, set this all equal to 0. And now in our case, it's already done for us. And then do df dx. Take the derivative of this whole thing with respect to x. That will give us y cos xy. And then that's going to be 0. Then over here, this is going to give us plus ey over y squared. Then df dy is going to be x cos xy. And now over, once again, over here, we have negative 2y. Now over here, we're going to have the quotient rule. So the derivative of the top derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Like this. So again, since we're taking derivative with respect to y this time, we had x cos xy minus 2y. Derivative here. Again, derivative of x e to the y with respect to y is just going to be x e to the y. Denominator, numerator times derivative to the denominator, all that squared. And then just use our equation up here. Dy dx is negative df dx plus ey y squared divided by x cos xy minus 2y plus x e y squared minus xe y 2y. And we could make that into y to the fourth, huh? Like that. So again, always remember, you can remember how the order is by thinking that in your head that these could cancel, then we'd have dy dx. Just remember they can't cancel in reality. Then take the derivatives that you need. And then plug everything into this equation, and we get this. Now let me do the implicit differentiation with more variables. Let's do this problem here. Consider this problem, and we want the derivative. We want dz dy, and that's a misprint. And dz dx and dz dy. So once again, keep in mind what we want. We want to have dz dx, which means we're going to have df dx over df dz. And again, use your memory tool. If you were able to multiply, the delta f's would cancel, so to speak. And then for the other one, we're going to need dz dy is going to be equal to negative df dy over df dz. And so rewrite your function, set everything equal to 0. And that's supposed to be a z cubed minus log 3xyz. And this should be a negative as well. I messed that up quite a bit. So then just find your derivatives. df dx. And that's going to be 2y squared z cubed. Then take your derivative this with respect to x. Remember, it's going to be 1 over the argument times the derivative of the argument minus 6y. Then do df dy 4xy z cubed minus 1 over 3x yz. 10 to the inside. And that, oh, by the way, I made a mistake on the last one. Derivative to the inside should have included a 3, shouldn't it have? So in this one up here, why did the derivative this with respect to x, it should have been 1 over that times the derivative of the inside, which should have been 3yz. Almost made the same mistake here. So derivative with respect to y has to be 3xz minus 6x. Again, let's check that. With respect to y, 4xyz cubed, 1 over that times the derivative of the inside, which is 3xz minus 6x. Then finally, we need the f dz is going to be 6x y squared z squared 1 over 3x yz times the derivative of the inside, which is going to be 3 xy, and then the last one's going to be 0. And so just plug everything into the equation. It gets kind of long. dz dx is going to be negative this mess right here. And actually, we can cancel some of these things, can't we? We can actually cancel over here. We could cancel this yz, and we can cancel the 3 over here. So we put df dx in. We can make this minus in front, and it's going to be y squared z cubed, and cancel over here to be minus 1 over x minus 6y all over df dz, which is 6xy squared z squared. And once again, over here, we can cancel, can't we? We could get rid of this and this and this. So it's going to be like 1 over z, like that. Then finally, dz dy is going to be negative. And excuse me, like on this last one, that negative's like out in front. I don't know if that's clear there, but that negative is like out in front here. And same thing here, this negative is going to be like out in front. And so now we have to go back to df dy, which is at 4x yz cubed. And once again, we can cancel stuff here as well, can't we? We can cancel those out, so we end up like with 1 over y. And then minus 6x. And then in the denominator, we're going to have 6xy squared z squared minus 1 over z with a negative in front. So in this one, for the next problem here, we're going to do this problem for Lagrange multipliers. Use Lagrange multipliers to find the maximum and minimum of values of this function, if they exist. Sometimes they do exist, sometimes one of them won't exist. Of this function subject to the constraint x cubed plus y cubed is 16. So let's go ahead and do this problem. So again, kind of write down what our functions are. One is f e y e to the xy. The other one is g. That's our constraint. We always make g the constraint. And you can either write this as x cubed plus y cubed equals 16, or you can just set that all equal to 0. Like this. Then you can find like the gradient of f is going to be y e xy and x e xy. And do the gradient of g, 3x squared, 3y squared, like this. And then, remember, the next thing we want to do is set this up like this. Remember, in this case, lambda is a non-zero constant. So we're always allowed to divide by this. And so we want to set these two up. So then go to the next step. And so let's substitute this over here. So all I did was substitute our gradient of f and gradient of g. And of course, that's going to give us y e x y, x e x y. 3 lambda x squared, 3 lambda y squared. And to remember, make corresponding coordinates equal. And that's going to give us y equal xy equal 3 lambda x squared, x equal xy equals 3 lambda y squared. And to remember, when we set these up, these become two of our equations, and the other one's always the constraint. Always put the constraint, the original constraint in. Again, sometimes it's helpful to name these. Maybe call this equation 1, equation 2, equation 3. Again, these are what's going to be solved. And now, again, before we solve, we might end up wanting to divide by x or y. So we need to justify that x and y aren't going to be 0. Now, note in equation 1, if you recall, e to any power is never 0. And remember, lambda is always a non-zero constant. So e xy not 0, and lambda not 0. And so neither of those can be 0. Therefore, if y is 0, that's going to make this whole side 0, and it's going to force x to be 0, and vice versa. If x is 0, y has to be 0. And vice versa. So if we did have that case, so that would be true, but from equation 3, if we put zeros in here, we would get 0 cubed plus 0 cubed equals 16. So, and of course, 0 can't be equal to 16. So that tells us, so we have like a contradiction. So that means that x and y cannot be 0. So x is not 0 because that would force y to be 0. And if they were both 0, we'd have this contradiction. So that'd be like a simple way that you could justify that x and y can't be 0. So now we have the freedom to divide by x and y if we want to. And so let's look at equations 1 and 2. So if we go back and look at equations 1 and 2, we can solve each of those for lambda. And now, since this is lambda and this is lambda, we can set these equal to each other. Like this. And then notice, now we can cancel the e's because remember, they're never 0, so we're allowed to cancel those. And let's see, is there anything? We could also cancel the 3's. And so that's going to give us x over y squared is equal to y over x squared. And then we can cross multiply. We're going to have x cubed equals y cubed. Now notice what our third equation was. It was exactly x cubed plus y cubed is 16. So we can substitute into that equation. And you can go do it in either direction. I'll replace y cubed. So sub into equation 3. And that's going to give us x cubed plus x cubed equals 16. That's going to give us 2x cubed is 16. That's going to give us x cubed is 8. And of course, the cubed root of 8 is in fact 2. So that means x is going to be equal to 2. And now notice up here, x cubed is equal to y cubed. So that means y cubed is also equal to 8, then also y is going to be equal to 2. Like that. So we have the point the 0.22. So will this produce a max? Or a min? So first of all, let's put its value in. Let's substitute into the function. So put the 0.22 into our function. Again, remember our function was e to the xy. So it'll be e to 2. That's going to give us e to the 4. So this is the function value at that point. So again, is this a max or a min? All we have to do is pick any other point that satisfies the constraint. So pick a point that satisfies this. And let's see, what would be, of course, it's going to have to be a different point than 2, 2. Let's see, what could we pick here? You could maybe pick, so this has to end up being 16. And let's see, maybe the simplest thing would be to pick x equal to the cubed root of 16 and y equals 0. Because notice that would satisfy our equation. Because see, we would have, if you put this in here, that's going to, if you cube it, you're going to get 16. So now check that in the function. 16 thirds and 0. So that's going to be 16 to a third times 0. That's going to be e to the 0, which is 1. So that was less than we got from the Lagrange. So this is less than this. And remember, we said the Lagrange will get you either a max or a min. And so therefore, we determined that there was a point on the constraint that gave us something less than we got here. So that means that this is a max. Remember, if we had had 2 points and they came out and they produced different function values, then we could conclude that one of them was a max and one of them was a min. But this time we just had 1 point and it gave us just one function value. And so we had to pick another point on the constraint and see if that value ended up greater or less than we found here. It ended up less than, so that means that the point we found had to be a max. Let's take a look at this problem here. Find the directional derivative of the function given by this at the point 2, 1, 0 in the direction of the vector 5, 3, 2. So let's take a look at this. And you can do this in a different order, depending upon what your preference is. When I did it previously, so I started with finding the unit vector in the direction of this vector. So we want to find the directional derivative in this direction. So we need to find the unit vector in that direction. And so it's going to be 5 squared plus 3 squared plus 4 squared. So it's going to be 25. Excuse me, this should be 2 squared. I'm getting a little ahead of the game. 2 squared. So it's going to be 25, 34 plus 2 squared, which is 438. So this is a square root of 38. So a unit vector in the direction which we want to go is going to be given by this. That's going to be 5, 3, 2 divided by square root of 38, which is equal to 5 square root of 38, 3 square root of 38, 2 square root of 38. And then take the partials. EZ. This, so we went back here and took the partial derivative of this with respect to x. Got this. Then we'll need the partial with respect to y. That's going to be 0. We're going to have 2xz. And then that's going to be 0. Then finally want to find fz. That's going to be x e to the z plus 2xy minus 3. Those are our partials. And we're going to put that in the gradient. Now we might as well go ahead and find the, we'll go ahead and find the values at the point given of each of these. So let's evaluate this. So we want to find the directional derivative at this point. So put those values in E0 plus 2, 1 times 0. That's actually going to end up giving us, this is going to be 1 plus 0. It's just going to be 1. Fy at 2, 1, 0. That's going to be, when we put 2, 2, and that's going to be 0, huh? Finally, f of z. This is going to be at 2, 1, 0 again. That's going to be 2 e to the 0 plus 2 times 1 minus 3. So that's to be 2 plus 4 is 6. Looks like that's going to be equal to 3. And that's going to be our gradient. And so we have everything we need. So remember, the directional derivative at that point is going to be the gradient evaluated at that point, dotted with the unit vector And the gradient we found was 103. Dotted with this value up here. 5 square root of 38. 3 square root of 38. 2 square root of 38. 5 square root of 38 plus 0 square root of 38 plus 6 square root of 38. And so it looks like it's going to be 11 over the square root of 38. And remember, directional derivative says this is going to be the derivative at the point 210 in the direction of this vector 5, 3, 2.